We are returning to what we started really at the beginning of the semester, which was sets and set operations. But the difference is now we will prove things about sets, and we will use the techniques we have been discussing in the recent lessons. So the first one I will prove is here. It says for A, B, and C sets, if A is a subset of B and B is a subset of C, then A is a subset of C. Now, you might think, or you should think really, I can draw a Venn diagram and illustrate what's happening here. So say I have some universe U, and let's draw a Venn diagram. Well, I have A, and A is a subset of B. This is the first assumption here. And then this part, it says B is a subset of C. So this means C sits out here. And can we conclude that A is a subset of C? Certainly it looks great in terms of the Venn diagram. But Venn diagrams are for visualizing and illustrating, and they are not set theoretic proofs. So quite often, we will have a statement we're trying to prove about sets, and you can sketch a Venn diagram to get an idea about the statement. But then a set theoretic proof must follow. Let me interject to ask a question, and that is, how do we prove A is a subset of C? And I mean generally. So if I hand you a set A, hand you a set C, and you are asked to prove A is a subset of C, how would this go? Well, the answer, complete sentences, of course, but I mean more than that. From a logic standpoint, how would we formulate a set theoretic proof of this type? So let's remember from the first week of class what this means. This says every element of A is an element of C. And I can write that as follows. If X is in A, then X is in C. This implication is really what this means. It's an implication. And we have been, in the last few lessons, discussing techniques on how to prove an implication. So the answer is we prove the implication, which is X in A implies X in C. Back to the first example. We assume A is a subset of B and B is a subset of C. Now, this is what I'm trying to show. We could, in fact, label this. This would be my P, and this would be my Q. I'm trying to show a P implies Q. And I'm doing this directly, so I'm assuming both of these. And then I want to show A as a subset of C. To show this, like I said, it is an implication. So let's just let X in A, and we need to show X is in C as A is a subset of B and X is in A. Well, remember, this means that X is in A implies X in B. So we have X is in B. And then the next statement is almost the same, as B is a subset of C, and we've already justified X is in B. We have X is in C. Therefore, well, you see, this is what I wanted. I wanted to show X is in C. So maybe I will just make a final statement. X is in A implies X is in C, meaning A is a subset of C. And this is the end of this proof. Here's my next example. If A is a subset of B and A is a subset of C, we want to prove A is a subset of B intersects C. Now again, let's draw a Venn diagram to visualize what's happening, and then we will give a set theoretic proof. So I have a set A. This is what I am starting with, and here is some universe. I know A is a subset of B, so B is something like this. And I also know A is a subset of C. So C would be something like this. And then I want to conclude A is a subset of B intersects C. We certainly see it in the Venn diagram. We certainly can visualize this theorem, right? So now let's give a set theoretic proof. We assume A is a subset of B and A is a subset of C. And then I want to show this. So this, which is, just as we discussed in the last one, this itself is an implication. And this is what I want to show. So let's let X be an element of A. And to get this subset equal to, I need to show X is an element of B intersects C. Okay? Well, X is in A. As A is a subset of B and X is in A, we have X is in B. Similarly, as A is a subset of C and X is in A, we have X is in C. So now let's look what we have here. Thus, X is in B and X is in C. And this is the exact definition of B intersects C. X is in B intersects C. And this is what I was trying to show. So I could just end and put a box. Maybe I will just say, therefore, A is a subset of B intersects C. This is our second set theoretic proof. Here's another example. This one I like because, well, I like most examples, but this one I will give two different proofs, which makes it super cool in my opinion. Here we have two sets sitting inside some universe. If A is a subset of B, we want to prove B complement is a subset of A complement. And again, we can get an idea. We can visualize. Here's my universe, and A is a subset of B is like this. And then if you think about complements, B complement is everything in U that's not in B. And so that sits out here. All of this outside B is B complement. And this should be a subset of A complement. And maybe I won't shade anymore, but ask yourself, do you see that here? Well, yeah, because A complement, you go from this, I'll maybe make it black, from this inner circle and include everything that is not in A. And so we do visualize this relationship in this Venn diagram. But now let's prove it. So like I said, I will give two proofs. The first proof really uses things we have discussed. So we assume A is a subset of B. And then we want to show B complement is a subset of A complement. But what does this mean? A is a subset of B. It means for, let's see, X in my universe, X in A implies X in B is a true statement. That's exactly what this means. Now, this is logically equivalent. I'll say this implication is logically equivalent to, well, it's contrapositive. This we know. In fact, this is what gives us the entire proof by contrapositive technique. and it's contrapositive, well, look at the implication. It would be X not in B implies X not in A. And this is for X in the universe. So this means this is a true statement. And now if I just unravel this, I'll say restating. We have for X in U, X not in B means X is in B complement, and X not in A means X is in A complement, is true because it's logically equivalent to our assumption. And this completes the proof. This is exactly the statement that B complement is a subset of A complement. This is one proof. Proof number 2. We will prove by contradiction. Well, let's back up for a moment and figure out what our assumptions will be in a proof by contradiction. We are trying to prove an implication. Here is the if, and here is the then. Okay, P implies Q. In a proof by contradiction, we would assume, maybe I'll put this in parentheses, we assume P and not Q, right? Because we assume the implication is false, equivalently that the negation is true, and the negation of a P implies Q is P and not Q. So let's write that in this case. We assume P is true, A is a subset of B, and we assume Q is false. B complement is not a subset of A complement. Now, let's look at this. We know what it means to be a subset. It says, well, if this was subset, it would say every element of B complement is an element of A complement. So with not a subset, that would say there is at least one element in B complement that is not in here. So let's write that. Then there exists an X in B complement with X not in A complement. Now let's just restate this about this X. We have X is not in B. That's this statement, right? About being, if you are in B complement, then you are not in B. So that's this restated. And this, if you are not in A complement, then you are in A. So, and X is in A. Now, we have to also use this. We are about to arrive at our contradiction. We also have this. So as A is a subset of B, we see X is in B. Now we have our contradiction. This contradicts that X was not in B. And this is the end of this proof. So this statement we have proved two different ways. Here's my next example. Again, it's about subset. So very soon we will prove some statements about set equality, but let's do another example regarding subset. So we want to assume A is a subset of B and C is a subset of D, and then prove this, A cross C is a subset of B cross D. We assume, just as I was saying, A is a subset of B and C is a subset of D. Then we let X be an element of A cross C. And our goal is to show X is an element of B cross D, right? This would say exactly this. Well, let's use the definition of what this Cartesian product is. There exists an A in A and C in C with X is equal to this, A comma C. Now, we have to use our assumptions. As A is a subset of B, we have little a is an element of B right here because it's an element of A and A is a subset of B. And then as C is a subset of D, we have little c is an element of D. So then this element X, which is AC, but we have justified A is in B and C is in D, meaning that X itself is in B cross D. And this is the end of this proof. Now let's prove two sets are equal. And the first example, we want to prove the set of integers X such that 3 divides X. This is A. We want to prove that's equal to the set of integers such that X can be written as 15n minus 9m for some n m in integers. We want to show these two sets are equal. Well, just like when we were first about to show one set with a subset of another, I took a moment to talk about what that even means, and let's do that here. Two sets are equal, this we have discussed, provided they have the same elements. Or another way to say that, generally we show two sets are equal by showing two things. First, that A is a subset of B, and second, that B is a subset of A, right? Because this would say they have the exact same elements. Another way to think about this is this is really an if and only if. So A equals B is equivalent to saying that X in A if and only if X is in B. This was the most recent thing we did was if and only if proofs. And now we get to do more of them with set theoretic proofs, showing two sets are equal. It's an if and only if. And as we know, there's two directions. You assume X is in A, show X is in B. That's this number one. And then you assume X is in B, show X is in A. And that's this number two. And so this is how we show two sets are equal. Now for this example, first I will show subset in this direction, and that is this direction of the if and only if. So we will let X be an element of A and show X is an element of B. And both of these we have to unravel what it means to be in these two sets. And just as a comment, I'm not drawing a Venn diagram here because given these sets are defined with set builder notation, I'm not sure how to even sketch a Venn diagram, and so I will just jump right in to the proof. Let X in A. Well, then we see the definition of A. There exists, say, Y integer with, well, 3 divides X, so 3Y equals X. This is what it means to be an element of A. Now, I need to find integers n and m such that 3y is 15n minus 9m. And then I will be able to conclude X is in B. So if I think, let's see, 18 minus 15 is 3, and that can help me here. So then X, which is 3y, okay, I can make 18 and then minus 15. Okay, like this. Now let's check. We have minus 15, we have plus 18. So in fact, we do have 3y here. And so look, x is 15 times an integer minus 9 times an integer. I just need to make that observation where minus y and minus 2y are integers. This shows x is in B. Okay, so I have the subset in one direction, and now I need to do the other direction, which in my opinion is slightly simpler. I need to let x in B and show x is in A. Okay, now we use the definition of B. There exists, we will say P, Q integers with x equals, it will be 15p minus 9q. And this equals, let's factor out a 3 from both. This is 3, 5p minus 3q. Now you see 3 divides x because 5p minus 3q is an integer. And this means x is an A. And this is the end. I have proved both directions. Subset in each direction, and so I have proved A equals B. If you want to just add a comment about that at the end, you certainly can. Therefore, A equals B. And this is our first proof of two sets being equal. Here's another example where we will prove two sets are equal. And this is one that we can illustrate with a Venn diagram. So we have A and B. Here's my universe. And then we want to, I will work with the left-hand side and shade, and we should see all of A shaded in. So the first is A minus B, which is you take everything in A, and then you remove from B. That is what I am shading in pink. This is A minus B. And then union A intersect B. A intersect B is here. You see, visually, we get all of A, but now let's give a set theoretic proof. We have two directions. First, I will show subset in this direction, so I let x be in this set on the left, which would be A minus B, union A intersect B. Now, this is an OR. Then x is in A minus B, or x is in A union B. Well, when we have an OR as our assumption, we need to break this into cases. Case 1, x is in A minus B. Then, well, in particular, x is in A, but I will write out A minus B means x is in A and x is not in B. So in particular, x is in A, and this is what I am trying to show. Case 2, x is in A intersect B. Well, then x is in A and x is in B. And again, in particular, we have x is in A. So in either case, we see x is in A, and this really concludes the subset in this direction. Now let's go the other way. Let x be in A, and we want to show X is in this, which is A minus B union A intersect B. Well, you see there are two cases here, really two. There are two possibilities. Either X is in B or X is not in B. Case 1, X is in B. And then, well, we already have said X is in A, so then X is in A intersect B. And case 2, X is not in B. These are the only possibilities for X. You're either in a set or you are not. So X is either in B or not in B. And in this case, well, we know X is in A, and then X is not in B. It says X is in A minus B. And so, altogether, we see X is, one of these two cases happen, so that says X is in here, or X is in here, which says X is in the union. A intersect B union A minus B. And this completes this direction. So therefore, we have shown this, A minus B union A intersect B equals A. Okay, this is the end of this proof. I will end today with a comment, but also an example. I want to comment about this homework exercise that is for you, and that is for A, B sets. Prove A is a subset of B if and only if A minus B is empty. And this is of the form P if and only if Q. Now, I'm not going to work this problem because, well, as I said, that's an exercise for you. But the comment that I want to make is showing a set is empty. Generally, how do we show a set is empty? Well, you see, this is not brand new. In fact, on our contradiction day, I actually did an example showing a set was empty. To show a set is empty, typically, contradiction. You assume the set is not empty. This is typically the easiest way to go about. You assume the set is not empty, argue until you reach a contradiction. But a hint to the homework for this direction, which is P implies Q, I would use contradiction. And when you do, the assumption is P and not Q. And so this would translate into A is a subset of B, and here we are assuming this is not empty. And then you need to argue until you reach a contradiction. So that is the end of the hint to my homework, and I will, or your homework, and I will not do any more so that you can work. But let me just, the final thing we will do today is we will show for any set A cross the empty set is the empty set. Okay, this I mentioned when we were doing Cartesian product at the very beginning of the semester, but let's actually prove it by contradiction. And like I said, this is an example of this comment showing the set is empty using contradiction. So by contradiction, we assume that A cross the empty set is not equal to the empty set for some set A. Then, well, if it's not empty, there's something in it. So then there exists X in this A cross the empty set. We may find little a in A and little b in the empty set with this X is this ordered pair. This is definition Cartesian product, that this set consists of ordered pairs. Well, you see, we have an issue. We already have our contradiction. I just need to write it. We have an element in the empty set. So this means the cardinality of the empty set is bigger than or equal to 1, because here is an element in the empty set, and this is a contradiction. The empty set has cardinality 0. So this was just an example of using contradiction to show a set is empty.